My name is Benjamin, and I'll be presenting today about improving reasoning with multi-agent systems. The goal of this project is to combine and adapt Reason LLM and RL techniques to fine-tune the Qwen 2.5 0.5 billion parameter base model for math reasoning. It's an important problem because most people don't have the compute for larger models, and it's especially important for researchers to have new techniques to try on smaller models before they can scale them to larger models. Math reasoning is an interesting problem because it's so challenging for LLMs, especially smaller models. It's a skill that helps unlock several more advanced capabilities. The tasks in this dataset are based on countdown. In this dataset, the model gets a target number and needs to use the other numbers exactly once in a mathematical expression that equals the target. If the model outputs a correct equation, it gets a score of 1. If it outputs an equation with the wrong numbers or that doesn't equal the target, it gets a score of 0.1. Otherwise, it gets a score of 0. One of the things we realized was that it's hard to generate correct responses every time, so instead, we generate k responses and pick the best one. Picking a response is also a complex task, so we split it into extraction, evaluation, and selection, each with a separate LoRa adapter for training. By separating the tasks, each of the agents can independently improve, even if the other agents are lower quality. This is accomplished by having each agent's loss function be based on what the ground truth would be if its inputs had been correct, instead of what it should have been if all of the agents had output correctly. This also helps us debug where the system makes a mistake. For example, if the selector agent chooses an incorrect example, but the critic agent said it was correct, that means the critic agent needs to be improved, and the selector agent is not penalized for that. So let's walk through an example. In this example, the input was 1, 86, and 97, and the target was 10. First, the generator gets this input and outputs 16 different chain-of-thought responses, each with think and answer tags. The extractor extracts the answer portion and invokes the calculator tool by adding an equal sign at the end. The calculator tool computes the expression value and appends it to the response, like in this example. Because the extractor agent was often the worst performing agent, we also implemented an automatic extraction that would programmatically extract the answer and compute the expression value. The critic evaluates if the expression value matches the target and if each number is used only once. It runs each answer with the expression value in a prompt through its model and whichever of correct or incorrect has higher logits for the next token. We then prepend the correct or incorrect evaluations to the extracted answers for the selector agent to choose the final answer output by the system. The selector agent can also choose to output none of them if it thinks all the responses are incorrect. Here are some results. We evaluated our system with both agent extraction and automatic extraction with two different base reasoning models, and compared it against the base model results. The base model for the generator agent was SFT fine-tuned on a countdown-like dataset, and another version was additionally fine-tuned with DPO and countdown. The other agents use a base model fine-tuned on Smalltalk for instruction following. With agent extraction, the system was similar or slightly worse to the base reasoning model. With automatic extraction, we saw substantial improvements, especially for the SFT base, which improved from a score of 0.32 to 0.62. We believe it's because the SFT base is inconsistent and only sometimes generates good responses. Using 16 samples allows the multi-agent system to identify a good response. When we tried using a single prompt to extract, evaluate, and select, the performance was extremely poor. So splitting into subtasks was important, even without fine-tuning. Similarly, adding examples to the prompt was critical for the agent to understand the task, especially without fine-tuning. When implementing the agents, we saw that the extractor agent was very hard to tune. We needed to repeat the instructions for invoking the calculator tool several times into the prompt before the model figured it out. The multi-agent system also has a few different points of failure. In particular, the extractor agent was usually the lowest performing agent, so the critic and selector often got bad data. As a result, the output of the whole system was sometimes incorrect. With these results, we did not fine-tune the agent models at all, but we expect this to provide a significant boost in performance. We also plan to add multiple groups of agents and use multi-agent debate and majority vote, which will help add resiliency to prevent a single point of failure. Thank you for watching my presentation. I hope you enjoyed it.